This video will cover section 6.1 on matrix solutions to linear systems. When we covered section 5.2 on solving linear systems with 3 variables and 3 equations, I mentioned that we would revisit this topic in chapter 6 and learn how to use matrices to solve them and your calculator. And that is what this section will do. So in order to solve a linear system of equations, keep in mind that this method we're talking about only works for linear systems. So the nonlinear systems that we talked about in section 5.4 do not apply to this method. Okay, these are only for equations that have variables that are all raised to the power of 1. Okay, that's an important comment. All right, so we use what we call an augmented matrix to set these problems up. This is a shortened way of writing a system of equations. So if we have a linear system of equations that looks like this, say it's 3x plus y plus 2z equals 31, x plus y plus 2z equals 19, x plus 3y plus 2z equals 25. We can create what we call an augmented matrix. So a matrix is just generally a set of square brackets that includes rows of numbers, rows and columns of numbers. So to create our rows and columns, we're going to just look at the coefficients of the variables and the constant term. So our first row, we're going to take the coefficient of x from equation 1, the coefficient of y from the first equation, the coefficient of z, and the constant, and write them down in a row. So for equation 1, coefficient of x is 3, the coefficient of y is 1, the coefficient of z is 2, and the constant term is 31. So the first column is going to represent all my x coefficients, the second column will represent the y coefficients, the third column the z coefficients. You'll usually see this vertical line right here to represent the equal sign, and then the constant term on the other side of the equal sign. And then each row just represents the number of equations that I have. So if I have 3 equations involved in my system, I'm going to have 3 rows of the augmented matrix. So rows move horizontally, columns up and down. So our goal is, once we have set up our augmented matrix, is to use what we call matrix row operations to rearrange this matrix to a new matrix in one of these 2 forms. So we can solve if we can create a new matrix that's in what we call row echelon form or reduced row echelon form. So row echelon form means that I have created a new matrix where on the left side of my equal sign we have this main diagonal that consists of all 1s. So 1s along my main diagonal. Below the main diagonal we have this triangular region that contains all 0s, so a triangle of 0s below the diagonal. And if I can get it to that point, then we can solve by what we call back substitution. So in other words, this matrix would translate back to equations as 1x plus whatever a is times y plus whatever b is times z equals c. The second equation, there's a 0 here, so this would just mean 1y, or y, plus d times z equals e. And then my last equation, there's a 0 in the x and a 0 in the y column, so this would just mean 1z, or z, equals f. So if we get that lower triangle of zeros, it'll tell us the value of z. We can substitute that in here for z and solve for y. And then once we find y, we can substitute both z and y up here and solve for x. So that's why it's called back substitution. All right, the other form we call reduced row echelon form, and it takes the matrix row operations a little bit further. It still creates a diagonal of 1s. You still have this triangle of 0s below it, but you do a few more row operations and create also a triangle of 0s above it, if possible. So reduced row echelon form produces 1s along the main diagonal. It has a triangle of 0s below and above that diagonal. And in this case, we don't have to do back substitution because this one is already solved. notice that the first equation would translate back as x equals a, because there are no y's or z's, because these are zeros. This one, there are no x's. This would mean 1y, no z's, so y equals b. And then finally, my last equation, if there's no x's or y's, this would mean 1z, or z equals c. So if I get it to reduced row echelon form, I could just translate back and write down my answer, A, B, and C. All right, so what are the row operations that we're allowed to use to get it to the form we need? It's basically models the same steps that we follow when we solve a linear system by the elimination method, like we did back in section 5.2. We're just applying those steps to the numbers in the matrix instead of the entire equation. So I can take any two rows of the matrix and interchange them. All that really means is you can rearrange the equations in any order that you want. Step 2, or the second option, we can take elements in any row and you can multiply or divide them by any non-zero constant. We do that when we solve by elimination. If we have to create opposite coefficients in front of two variables, we might multiply an entire row by a -3, or we might multiply a whole row by a 4. So that's really all that this means. And then the third option, you can take elements in a row, multiply them by a constant, and then add those results to the corresponding elements in another row, right? We do that when we solve by elimination. We multiply through by a constant, and then we add equations together, and we end up eliminating a variable. So it's the same steps, it's just written in a different format. Okay, so our goal here would be to try to take an augmented matrix, such as this one, and use those row operations to try to create ones along the main diagonal, zeros in the triangle below, and zeros in the triangle above. So before we start to do this next example, let me just talk about a few comments here about notation. If we're asked to, or if you're indicating that you're going to take two rows of a matrix and interchange them, the notation would be Ri switch with row J, so like R1 switch with row 2, R2 means flip them around. Multiplying a row by a constant, you just put that constant times whatever row you want to multiply by. So if it said do 4R1, it means multiply all of R1 by 4. And then the combination, step 3, multiply a row by a constant and then add those numbers to another row, would look like this. And the result of doing this will replace the row you're adding them onto. So that would replace whatever row J was. All right, so here they're asking us to do exactly this third thing. So it's giving us this augmented matrix, and it says perform this row operation and write the new matrix. So they're telling us to take -3 times the entries in row 1, add those results to the entries in row 2, and then write down what we would get. All right, so the translation of this is multiply row 1 by -3 and add the results to row number 2. All right, so -3 times row 1. We put a -3, and then these are the entries in row 1. I've just written them down here. So when I do that, I would multiply -3 by each of those numbers. So -3, +3, -15, and +18. Then I take those results and add those on to what was in row 2, which was 3, 3, -1, and 10. So 3, 3, -1, and 10 get added on to these numbers. So that gives me a 0 right here, a 6, a -16, and an 18. So this would become my new row number 2. So I would retype row 1 just as it is, replace row 2 with my results, and then row 3 was not affected. So this would be my new matrix. Notice this row operation has started the process of getting to where I need to be. I have a 1 up here in this upper left corner. We would start by trying to use it to put zeros in the 2 spots below. Right? So that would be the same as taking, right, this equation and trying to eliminate x with the first 2 equations. Multiply this by -3 and add. If I was to keep going, I would take the top equation times -1 and add it to the bottom to put a 0 in that spot. And then I would move on and try to get row 2 to, or column 2 to look the way I need it to be, and then finally column 3. So you can continue to apply the row operations to this matrix until it is in reduced row echelon form. But as we can tell by just talking about that process, this is time consuming. Okay, this is not fast and simple. So if you do not have a graphing calculator, I would suggest here this problem is all you are asked to do. So this would be the answer. But if you're solving a system completely, I would just do it the way we did it in section 5.2. I wouldn't try to mess with using a matrix unless you have a graphing calculator. All right. If you have a graphing calculator to solve the system, it can do it for you, but you have to tell it what to do. All right. To solve a linear system using matrices on your graphing calculator. So these steps are specific for the TI-83 or the TI-84. If you have a different version of a graphing calculator, it probably has the capability of solving a matrix. It's just that the menus might be in different places and there might be a different sequence of steps to follow. So you're just going to have to figure that out on your own or go to the Success Center and they might be able to help you. But if you have a TI-83 or 84, this is how it's going to work. So you're going to start by pressing second. So that's this blue button up here. And then the X to the negative first key is down here, right here. And notice I wrote matrix underneath because that's after you press second, you're accessing the matrix menu when you do that. Okay, and after you press that second and then this key, you're going to scroll over to edit and then hit enter. And then once you do that, you're going to be asked, you're going to see this screen right here. It's going to say matrix A. And then you're going to have to enter the number of rows and the number of columns of your matrix. So in our case, we would have 3 rows and 4 columns. So I have to tell it 3 and then by 4. That's what this means. It would translate to 3 by 4. Row first, column second. And then you'll see this screen right here. Okay. Once you get to that point, you're going to type in the entries of your augmented matrix. So I just put in that previous problem, the original augmented matrix that we were given. So 1, enter. You'll scroll over here, -1, enter, 5, -6. And you just keep going until all these boxes are filled in. So once you have the screen looking like this, where all the boxes have been filled in, if you're on a TI-83 or an older version, your screen will look a little different because it's not condensed with the same formatting, but it still will give you places to type things in. You might have to scroll off the screen and then come back to the next row, but it should still work the same way. It just might not look exactly like this picture. So once you've got all of your numbers in place, the next step is to hit second again, and then the mode button because you want to quit. You want to go back to the home screen. So second mode or quit, this will take you back to the home screen. All right, so once you are back to the home screen, again, you're going to go back to your matrix menus. You're going to hit second, that X to the negative first again to access your matrix menu. This time, once you do that, you're going to go to the middle column that says Math, and then scroll down until you come to the option B, which is the command RREF, and it'll have an open parenthesis. That stands for Reduced Row Echelon Form. That's the one that solves it all the way. And then press Enter. So you'll get to Math. Once you get into your matrix menu, you'll be here. You'll scroll over to Math, and this is what you're going to see. Down part B here, be RREF, that's what you're looking for. So after you do that and press enter, you should see RREF open parentheses on your home screen, because if you quit in that previous step, you would have been on your home screen when you accessed that. Okay, so once you see this on your home screen, your next step is to do again, second matrix or second X to the -1 to get the matrix menu. Just stay in that names column. You'll be in the names. You'll just see A, B, C, D, etc. and press enter because you likely stored your matrix as A. So then you'll see you already had RREF open parentheses. So when you press enter, when you're under that name A, it'll pull the matrix A into that space. So this will be on your screen now. Then you're going to close your parenthesis. Just close the parenthesis from here and press enter. And this is what should pop up. It won't be blue and pink like this. My printer was running out of ink, so it didn't print very well, but this should be what shows up on your home screen. So this new augmented matrix, 1, 0, 0, 1, 0, 1, 0, 2, and 0, 0, 1, negative 1, represents my equations, which are x equals 1, y equals 2, and z equals negative 1. We just translate the matrix back to equation form. So the solution to this system, this is the one we initially solved because the numbers I typed in were 1, negative 1, 5, negative 6, 3, 3, negative 1, 10, 1, 3, 2, 5. So that system has the solution set 1, 2, negative 1. So this is another case where if you have that graphing calculator, you can save yourself a lot of time on solving these problems if you can solve it using matrices. Without the graphing calculator, ignore the directions and just solve them the way we did in section 5.2. Okay, so let's try one more. We want to solve this system using matrices. All right, this one, notice my variables have been rearranged a little bit, so I can't create my augmented matrix until I rearrange. So I need to rewrite each equation with the x term first, followed by the y term and the z term equal to the constant on the other side. So this first equation, I'm going to leave the 2x, but I'm going to subtract the y and subtract the z over. So I'll get 2x minus y minus z, and we'll leave the 4, so equals 4. In this equation, I have my y and z on the left, but I need the x to move over there, so I'm going to add the x over. It has to come first. So if I add it over, it's positive x, so x plus y minus 5z equals negative 4. And this one, notice all the variables are already on one side and the constant on the other, so I can just list this side first. X minus 2y equals 4. There is no z in this last equation, and that's okay. So once I have it rearranged to where all the x's are listed first, followed by the y's, followed by the z's equal to the constants, now we can create our augmented matrix. So the first row would be 2, negative 1, negative 1, 4. The second row, 1, 1, negative 5, negative 4. And 1, negative 2, 0, because there is no z, and 4. So then we would go back through our sequence of steps to ask the calculator to solve it. So you would go back to those other pages and follow those steps. So you're going to start by hitting second, x to the negative 1, or second, get to the matrix menu, scroll over to edit, press enter. You won't have to change the rows and columns because this is still a 3 by 4, and you can just type over the previous numbers and put in your new numbers. Just override what was there before until it looks like this. So once you get that matrix inserted into the calculator, it's second mode to quit, take you back to the home screen. Then back to second, and then that matrix menu again, over to math, down to RREF, enter. That will pull the RREF command to your home screen. Back into matrix again, so second, x to the negative 1, stay in the names column this time, press enter, we'll pull this matrix, or it'll just say A, right, after the parenthesis. Close the parenthesis and press enter, and this should be the matrix that you see on your screen. So this would translate back as x equals 2, y equals negative 1, z equals 1. So your solution set would be 2, negative 1, 1. I should mention that in this section, all of your systems will have a single ordered triple answer. So you will get this left side of this, where this line would be, to be this diagonal of 1s with triangles of 0 above and below, which means this last column is your solution. Should also mention that in section 6.2 that we talk about next, we will look at what happens when you do the same process and how to know if you have a no solution system or an infinite solution system. But that will not matter in section 6.1. Everything will have a single order triple answer like this one does. And that is the end of this section.